So 1.3 exponential functions. An exponential function is defined as, first off, it's a function, and it's some initial value times some constant. Shouldn't say constant, but it's a constant to a power. All right, so this is the rate of growth or decay. And we can cheat a little bit. We can put a negative up here and make this some different value, and negative means it's 1 over, and get all sorts of goofiness that's going to happen. So what are the two types? We got growth. And that's where b is going to be greater than 1. And you got decay. That's where the absolute value of b will be less than 1. Why absolute value here but not here? Oh, that's a good question. This means I don't put a negative in here, ever. I mean, it's just always positive. So, yeah, nothing else to say. If it helps, that's what it means. All right, so let's play with it a little bit. So here we got an initial value of 2 and 3 to the x. The minus 4 screws with us. This won't exist in calculus almost ever. Just doesn't. I don't know what else to say. And what I want you to know is that e to the x looks like this, and it hits at, in this case, 2. Plug in a 0. 3 to 0 is 1. Initial value is 2. Oh, wait, minus 4, it's going to shift down. So just be aware. So 1, 2, 3, 4, it's going to hit here. I haven't put any negatives or anything. Yeah, then it's just going to be pretty steep because of the 2 out front, or the 3 here. But it doesn't really matter. It's just going to do something like that. There is an asymptote down here. Normally the asymptote is at 0. When you put minus 4, it drops down to y equals negative 4. Just the way it is, it just goes forever in that direction, but never catches up. You need to know this. You need to know this. If you don't, you've got problems on your hands. No question about it. Negative infinity to infinity for the domain, and then the range, negative 4 to infinity. Yeah, and like I said, a normal one, it's at 0 comma a and has an asymptote at y equals 0. We're going to be doing limits soon, so it's really nice to know that the limit as x goes to negative infinity is the asymptote. It tends to help people if they start putting that together early. So find the 0 of f of x equals 5 minus 2.5x algebraically and graphically. We'll do it algebraically first. The 0 is where it hits the x-axis, and that's when y equals 0. That's confusing for people. When y equals 0, what does x equal? That's the 0 of this. So 0 equals 5 minus 2.5 to the x. 2.5 to the x equals 5. Natural log of both sides. Why do we natural log it? We could log it anything, but we'll natural log it because now we can bring the x down. This is the kind of thing I will be doing on the fly. You have got to be good at it. And that's about 1.7. My old notes go 2 decimal places. I'm actually going to do it right on my calculator here. .756. Good habit to start doing everything with 3 decimal places. First time I did the notes, I didn't. Live and learn. So what's this look like? Well, it starts at 5. Yeah, I'm not sure where it starts. Plug in 0, negative 2.0 is 1. So 5 minus 1 starts at 4. Let me rephrase that. It hits at 4. Has an asymptote at up here. I think that would be at y equals 5. I have to think about this a little bit. I'd probably just play with the calculator, but here we go. We said it hits at 1.756, so it's going to come down right about there. And do that. So normal is like that. Negative flips it down here. 5 moved it up. So yeah, this is y equals 5. I had to stop and think that through. That's the horizontal asymptote. Yeah, better be quick for graphing these because you're going to be doing a lot of it. So rules of exponents. When you're multiplying the same base, x to the 7th. When you're dividing the same base, x to the 3rd. When you're multiplying to a power, x to the 10th. When they're being multiplied, you can distribute and get x to the 15th, x to the 6th, and you can also x to the 21st. Or we could have just gone 7 times 3 is 21. And we can subtract first this time, then go to the 3rd. So x to the 3rd to the 3rd, x to the 9th. And don't forget, we can write it as a negative exponent. And that works both ways. We can flip it from the bottom to the top, or if we have it on the top, we can write x to the 10th as 1 over x to the negative 10th. All this will be popping up a lot in your near future. All right, how do we model an exponential function? Sure as heck don't do it by hand. That would make me insane. Well, we can do it this way. We can say things like, let's make, and you have to say this somewhere in the problem, year 2002 is our 0 year. So therefore our A value is 287.9. And then you could do, you go to year 3 there, 290.4 equals 287.9 times B to the 1st, because that's year 1, which is just B, and then you divide that out. Helps if I don't screw up the numbers. And we get a 1.009. Right? Or we can do it by calculator. And by the way, we only use the first one, so it's not accurate. We should use all of them. Calculator. Let's see how that works. So quit out of that. Let's clear this out. So we're going to be using that in a second. And stat, edit, clear, enter. My computer froze. Yes, it did. See if it comes back to life anytime soon. Nope. So let's go back here. Try and find a spot where the light actually works. That, edit, L1. I'm going to go with 0, 1, 2, 5. It's not 5, it's 3. I could have put 2002 whatnot in, but just going to go with that. 0.9, 290.4, 293.2. I have a huge problem with my calculator in that it doesn't always read what I put in. So make sure you do it right. Now we're doing an exponential model, so stat, calc, and we got to find exponential. And that's exponential regression. That means model it. So I want to store it, alpha y1, and hit calculate. So I get almost the exact same thing. I get y equals 287.8 times 1.009 to the x. Pretty cool. And then what's population today? So it's year 2021. If that's 2 is year 0, then we go to 19. So alpha y1 of 19 tells us today population is 342.7 million. 342.7 million. And we did this yesterday, but I didn't save it. Let's see how accurate that is. United States population. And I know I have to share the screen. So share screen. Let's see, US 332 million. So that's not a very accurate number in my humble opinion. I believe the case for this is that the United States is a much more linear growth, which makes no sense. It should not be growing linearly, but it is, which is weird. So the reality is that exponential is not a good fit for this. That's what we do in mathematicians. We figure things out. Oh, so what other ways can we model exponential growth and decay? What's a half-life? Well, a lot of you seen this. Area equals PERT. So this is an exponential growth, but we can make this negative. We can change this value and just tie that whole b value into an e to the r. A lot of people like this because e is easier to work with once you get good at it. So we'll come back to this. You can calculate simple interest with how much you have is your original amount times 1 plus r to the t. Or you can calculate compound interest with how much you have now is your original amount. And this is where it gets fun. 1 plus r over n. Monthly would be a 12. Weekly would be a 52. Quarterly would be 4. Your bank usually does it monthly because you get statements every month. So that's n is the number of compounds. T is, of course, the years. Well, the time interest you're using, it's usually years. And R is the rate. And A naught is the original amount. By the way, get that down, A naught. That's how we say it. A sub 0 is tacky, say A naught. All right, so that's another way to do it. And what's a half-life? Well, we do a lot of math with this, especially in a chemistry class. So we say how long is it until half of the original amount? Now, this is something I cannot get students to understand. I just can't for whatever reason. But if you have a equals a naught in any of these, so let's go with e to the RT. And people always say, well, how much is there? I don't know. How can I just say half? Well, it's just a over a naught. Whatever the original was is 1/2. And that equals e to the RT, or it could equal 1 plus r. It could equal any of these. And off you go. Hey, I know what t is, I know what r is. I can figure out the rest. So a lot of people get bothered by that. What's the yearly percent increase in US population? Well, based upon what we have up here, 1.009, you could easily write this problem as the American population is whatever amount you're starting with from year to year, 1 plus 0.009 to t. Now people say, oh, that's not as good a model as this one, right? No, it's the exact same. It's the exact same. 1.009 to the t is the same as saying 1.009 to the x. So people get a little confused by that. What's the number e? Well, that's when we have continuous growth or decay. Well, I was nervous about spelling that. And there's no such thing as continuous growth or decay. It's what we call discrete. Every time a person is born, we don't have 10th of a person, 20%, 40%, hey, a whole person, right? You have discrete numbers, an entire value. So how can we use this? Well, with the size of the world's population, each person coming out can be modeled as continuous. If you're talking about chemicals decaying, well, you're down to the molecular level. From our perspective, there's so many molecules and atoms, you can get away with calling it continuous, right? So this approximates a lot of things. We don't ask, we just run with it. And last but not least, how do we approximate f of x? Well, we actually do something called taking a limit, but I'm not going to get into that. Let's just say, well, what's f of 2? You plug it in and you get 2.25. That's nice. What's f of 100? You plug it in, you get 2.705. What's f of 2.71828. You keep making this freakishly big, this becomes e. It is a continuous number that never repeats, right? And you can see because it's got some weird stuff going on here, and never ends, goes on forever and ever. It's very similar to pi. I believe they call it a transcendental number, but I'm not educated enough in the math world to know that. So that's it. That's a lot of stuff. I would make sure I get tight on this because you're going to need it all. This is all coming at you at some point in time this year. Happy mathing.